Hello, thank you for watching this video. So in this video, we're doing question 9 of May, June 2024, question paper mathematics paper 1. The topic are cubic functions. So let's go. They are saying the graph f is drawn below. E and G are the x-intercepts of f. Right? No problem. So you are told that the graph f, here is it. You can see f here. You're told that E and G are the x-intercepts. Right? No problem. Then they have given you the incomplete equation of f. So here's f. You don't have A, you don't have B, you don't have C, you only have D. What is D? D is the y-intercept. So it's this value here. It's this point over here. So you know along this line, x is 0. Along this horizontal line, y is 0. So the coordinates of this point is x is 0, and y is minus 5. The coordinates of E, x is minus 1, and y is 0. Here G, x is equal to 5, and y is 0. So you have the coordinates. You have these 3 points as your coordinates. Right? No problem. So they are saying, show that A is equal to... So let's go to 9.1. They are saying, show that A is equal to 1, B is equal to minus 3, C is equal to minus 9. So they are saying we must show that A is equal to 1, B is equal to minus 3, C is equal to negative 9. That's what they want us to show. No problem. How do we do that? So one way of showing this, we have the x-intercepts, right? So we can try to find the equation of f using the x-intercepts that we have, like we normally do. So you know that if you want the equation of a cubic function, it's going to be y is equal to a into x minus x-intercept 1 times x minus x-intercept 2 times x minus x-intercept 3. Right? You normally use this, I'll say this formula to find the equation of a cubic function if you are given the x-intercepts, right? No problem. So if you look here, you have 3 x-intercepts, right? If it's a cubic function, like this one, with 3 up there, it should have 3 roots, which it should have 3 solutions. It should have 3 x-intercepts, right? So of course, you did nature of roots. When you're doing nature of roots, you are doing those nature of roots for quadratic equations, or quadratic functions. So in that case, you know your roots can be equal, unequal, right? Others can be negatives, others can be positive. So that's the sort of situation that you can have. For example, if we look here, let's say we look at this here. So let's say this is your function g. You can see these have roots here. So it have real roots. Are they equal or unequal? One is negative, the other is positive. So they are not equal, they are unequal. Are they rational or irrational? We don't know. It will depend what those values are, right? No problem. But you can say one root is positive and the other is negative. I'm trying to say one is negative and the other is positive. So you did nature of roots and interpreted roots. If you have a situation like this, maybe, let's say your G now looks like this. So in a situation like this, you have a solution, right? This does have solutions. So it does have real solutions. So for this function, maybe g, right? You have real solutions. They are real. How many solutions do you have? This is a quadratic equation. And the quadratic equation have the form y is equal to ax squared plus bx plus c, right? So the highest power of that polynomial is 2, which means there are 2 solutions. There were 2 solutions here. They were not equal. They were unequal there. So you also have 2 solutions here. But here there are what? If you see, if your solutions are also a turning point, so at that point, you have more than one solution, right? So in this case, the solutions that you have there, you have 2 solutions. They are real solutions, they are 2 because you are dealing with a quadratic function. But those 2 real solutions are equal. So your roots for this thing, they are real equal because both of those solutions are sitting there. And then now, the third situation that you dealt with might be something like this. You can see that this function of yours, your parabola here, does not touch the x, does not cross or touch the x-axis. So this thing will not have solutions because if you're looking for solutions, which is the roots of an equation, you're looking for the y-intercepts. So if it's not getting even there, the discriminant of this thing is less than 0. So when you find a discriminant of something less than 0, just know that it never touches the x-axis. It looks something like this. So coming back to this, the highest power is 3. So, which means we have 3 real solutions here. What do we have? We have 3 real solutions. And those solutions that we were talking about are your x-intercepts, which means we have 3 x-intercepts. But you can only maybe by your eye see 2, right? Which is here and there. But look at this point here. This point is an x-intercept and also a turning point. This point is an x-intercept and also a turning point. This is a similar situation here. This is an x-intercept and also a turning point. And we said we have 2 real roots there and they are equal. So this is the similar situation. We have 2 points there that are your x-intercepts. So the x-intercepts at this point here on this function, one is x is equal to minus 1. First one. The other one is also x is equal to minus 1 because we have 2 here. If you have a point on the y-axis, that is the x-intercept and the turning point, then you have 2 intercepts there, as you can see there. And the third one is that x is equal to 5. So these are x-intercepts. X equal to minus 1, x equal to minus 1, and x equal to 5. That's what you have. That is what you have. So what I'm trying to say is, just because you see 2, it does not mean there's 2. Where there's a turning point, know that you have 2 equal roots at that point. There at x equal to minus 1, you have 2 equal roots. So these are your x-intercepts in total. There's 3 of them. So now if you want to find the equation of this function f of x, we use this formula here. What is our y? Our y is our function, f of x, right? So we'll say f of x is equal to a into x minus x-intercept 1. What is x-intercept 1? X-intercept 1 is minus 1, right? So it will be x minus 1 times x minus what? X minus x-intercept 2. What is x-intercept 2? It's also minus 1 because there are 2 roots at that position. There are 2 equal roots at that position. So x minus negative 1. X minus the third root or x-intercept is minus 5 that you can see over there. So there's 2 of them here, there's 1 there. So you have x minus 5. So what you have f of x to equal to a into x plus 1 times x plus 1 times x minus 5. Right? Now, the challenge that we have now, we don't have the value of a. How do we find the value of a? If you are looking for an equation of a function and you get to a point like this, where, because how does an equation look like? Equations, normal equations or your equations are expected to contain maybe x only, y only, or x and y. Things like a are not supposed to be part of the equation. Things like r are not supposed to be part of the equation. Things like d are not supposed to be part of the equation. So you should only have the variables as part of your equation of a function. So in this case, a is not supposed to be here. So what we need to do, we need to find the absolute value of a, the value of a. How do we do that? You need at least 1 point to find the value of a. Right? In order for you to be able to find the value of a, you need to at least 1 point. So you ask yourself, is there any other point on your function that you can use to substitute as y and those x values there, so that you can be able to find the value of a, sorry. So let's look at our function. We have the 2 x-intercepts here and 1 there. We have only have y-intercept as well here. So we have the coordinates of this point. The coordinates of this point is what? Is 0 and minus 5. So we have the coordinates of the y-intercept. So what we can do, this is the x value and this is the y value. What does that mean? It means that if you start with the x value here, x value there, and x value there, the corresponding y value that we should get here, it should be minus 5. Because if this point 0 and minus 5 lies on this function of ours, if we substitute 0 here, here, and there, then the answer should be minus 5. Then we will only have a to find. Once we find the value of a, then everything else will come into place. So, what do we do? We say, okay, let's substitute our y there. So minus 5 is equal to a into x. What is our x? X is 0. So it's going to be 0 plus 1 here. And then we have another 0 plus 1. What else do we have? We have 0 minus 5. Then look, now we're left with a. So minus 5 is equal to, punch this in our calculator, this times that. You'll find a times, this is 1, this is 1, this is minus 5. 1 times minus 5. So this is minus 5. Then you divide by minus 5, divide by minus 5. Find that a is equal to what? Is equal to 1. Which is what they want us to prove over here. Now what are we missing? We're missing b now. How do we find b? What we need to do at this point, we need to take back this a of ours back here, this value of a, the absolute value of a, which is 1, and substitute back there, and multiply this bracket all out. Once we multiply this bracket all out, then now we'll be able to see the coefficient of x squared and compare to it whatever it is there. So let's do that. So we get that f of x, which is this, is equal to a. What is a? Your a is 1 into x plus 1 times x plus 1, x minus 5. So what I propose that we do, I propose that we multiply this bracket all out. Let's do that. Because once we multiply it all out, we'll be able to check each one of the terms that will come out of this and compare them to these values that are here. So let's go. So in that case, we say, okay, f of x is equal to, let's first multiply these guys here, the first two brackets. So if you multiply the first two brackets, you get that x squared, this time to multiply these brackets out, you know how to multiply these. X squared plus 2x plus 1. This is the product of these two, these three, this and that, times x minus 5, right? So f of x is equal to maybe x minus 5 times what? X plus 2x, x squared plus 2x plus 1. So we're going to multiply these two now. This and this are exactly the same, but just arrange them in an order that I'm comfortable with. So let's do that. So what do we have? So we have f of x is equal to, x will multiply all of these, right? So we'll have x multiplying what? X squared plus 2x plus 1. And minus 5 multiplying all of this as well, which means x squared plus 2x plus 1. Because you say x times this times this times that, which will give you, which is the same as this. This times this times this times that, which is the same as that. So let's go and find the answers to this. I'm going to clean that side because we don't need it anymore. So let's clean that side. Okay, so now, so let's try to find answers to this. F of x, which is this, x times x squared, that is x cubed, right? X times 2x plus 2x squared. X times 1, so it is plus x, right? No problem. Minus 5 times x squared, so it's minus 5 x squared. Minus 5 times 2x is minus 10x, right? Then minus 5 times 1, so it's minus 5. That's all we have. So let's collect the like terms. So f of x is equal to x cubed have no friends here, right? You can see 2x squared and this, so this is minus 3x squared. The x, this x goes with this one, this is minus 9x. The 5 have no friend, minus 5. So this is the equation of f of x. So the one that we're given this skeleton here, or this partial equation, or this incomplete equation. So the incomplete equation was what? Was f of x is equal to ax squared cubed plus bx plus, or bx squared plus cx minus 5. So you can see that the coefficient of this one is a. The coefficient of x squared is b, because you can look at x squared, there's minus 3, so that is b. Coefficient of x is c, and minus 5 is minus 5. So in this case, you can say, therefore, our a is a coefficient of x cubed is 1. The b is a coefficient of x squared is minus 3. And the c is the coefficient of x, which is minus 9. And this is consistent with what we're given, or with what they wanted us to show. So we've answered this question. So we're done with 9.1. We'll move to the next question, which is 9.2. I'm going to clean the board now. Okay, so now we're going to do 9.2. As you can see, I've redrawn the function f here, this cubic function of ours, and we managed to find a, b, c that we were asked to find from 9.1. So now, what I'm going to do, I'm going to use all this information that we know, including this one, to answer the next questions. So we're going to do 9.2 now. So 9.2 reads as follows. Calculate the value of x for which f has a local minimum value. So they want us to find the value of x, where our function f has a local minimum value. What is the local minimum value? A local minimum value is the lowest turning point of your function. Your local minimum value is the lowest turning point of your function. So this cubic function of ours have a turning point at E and the turning point here, down here. So the turning point at E, you can see is at a higher level, right? And the other one is at a lower level, here. So that one at E is called the local maximum of our function f. And the one down here is the local minimum. So what we're looking for here is the x value at which this local minimum is sitting at. The local maximum, we're given that the local maximum is sitting at x is equal to minus 1, at point E. So point E is sitting at x is equal to minus 1. So we have the coordinates at that point. It's minus 1 and 0, because that is the x-intercept, right? So now, they want us to find what is the x value at which this minimum is sitting at. That's what they're looking for. No problem. How do we find that? So, as you can see, like I said, here is the local maximum here. You look at this local maximum of yours. It's sitting here, this position here. It's sitting exactly at the x-axis. If you look at the x-axis, they are a tangent to this point. So the x-axis, if you look at them, they are a tangent to this function f, right? As they are a tangent, this tangent of ours is horizontal, right? So if a tangent is horizontal, or if a line is horizontal, you know what its gradient is. The gradient, if a line is horizontal, let me just write it on the side. If you have a horizontal line, let's say this line is horizontal, you know that a gradient of a horizontal line is 0. If a line is vertical, right, like this is a vertical line. The gradient of this function, we don't know, it is unknown, or it's undefined. You know that very well. So let's come back to this. So look at what is happening here. The tangent, the x-axis are a tangent to this function. They are just touching this function at that point, right? No problem. So the reason I'm telling you this is that at this point, the gradient of this line, the x-axis is horizontal. So the gradient of the x-axis is 0, because they are horizontal. They have the same orientation as that line. They have the same form as that line. Fine. Let's come back to this one. Let's suppose that you want to draw a tangent here. If you draw a tangent at a turning point of any function, if it's a function and you have a turning point, if you draw a tangent at the turning point, a tangent will be horizontal, which means the tangent will have a gradient of 0. The tangent at a turning point of a function have the gradient of 0, have a 0 gradient, because it will be horizontal. So, in that case, let's say we try to draw a tangent here. A tangent will be horizontal here at this point, which means this tangent of ours have a gradient of what? Of 0. You should keep that in mind. No problem. So when I was doing question 7, actually question 9, question 8, sorry. This should be question 9 here. So when I was doing question 8, I did explain, because we're doing derivatives from first principles, right? And we derived using the rules. So when we were doing the derivatives there, I did explain that if you find a derivative at a point, derivative at x, right? It gives you what? It gives you a gradient at point x. I told you that the derivative of a function gives you a gradient at a point, right? No problem. So now, if we can derive this function f of x and find its derivative, the equation, its derivative will be giving us a gradient at each and every point that we want. So, for example, let's do that. And say, okay, we have f of x to be equal to x cubed minus 3x squared minus 9x minus 5. So if we want the derivative of this, f prime at x is equal to what? We'll say 3 times 1, it will be 3x squared. And then minus 3, 2 times this minus 3, 2 times 2x, that 2 is minus 1. What is the derivative of this? It will be minus 9. 1 times 9 is 9x raised 0, right? And then the derivative of a constant is what? It goes to 0, right? Therefore, your derivative of f as a function of x is equal to 3x squared minus 6x, right? Minus 9. So what you have here is a derivative of your function f, right? This is the derivative. And I said that a derivative gives you a gradient at a point x, right? That's what a derivative gives you. It gives you what? A gradient at a point x. So now, at this point, you don't want a gradient at a point x, at a point, right? But you have a gradient that is 0 somewhere on your function. So what you want those x values that correspond to that gradient that is 0. Or you want the x values that will give you a 0 gradient. That's what you're looking for. So what is going to happen, we're going to say, okay, this f prime is a gradient, right? If f prime is a gradient, then we know that at this turning point, the gradient is 0, which means in the place of f prime, we can substitute our gradient of 0. Once we substitute our gradient of 0, then we can solve for the value of x. That will send us to the 0 gradient, or that will give us the corresponding values of, or we can find the values of x that will give us the point where the gradient is 0. So let's do that and say, okay, f of f prime at x is equal to 3x squared, right? Minus 6x minus 9. So we say that we know that this is a gradient at a point, right? And at our point where we want the x value for, the gradient is what? Is 0, because the tangent that you can draw at a turning point will be a horizontal gradient. It will be a horizontal tangent. So if it's horizontal, this gradient will be 0. So we put 0 here. The gradient at the turning point is equal to 3x squared minus 6x minus 9. Then you solve for x here. So what you do, take this to your quadratic formula, or you can just factorize it. I'll try that. Say 3 into x squared minus 2x minus 3. That's what you have. So 0 is equal to 3, and you factorize this thing further. So you have two brackets like this. You have x, you have 3, you have 1. So you have minus, you have plus. Therefore, 3 into x minus 3 will be equal to 0, or your x plus 1 is equal to 0. Therefore, your x is equal to 3, or your x is equal to minus 1. So the x values where the gradient is 0 is that x is equal to 3 and x is equal to minus 1. But look, I said this was a local maximum, and I said that this local maximum, the gradient is 0. Look, there is x equal to minus 1 because that's where another 0 gradient is sitting. So this should be the second one. And if you look at it, it's positive. It's on the right-hand side of your it's on the right-hand side of your y-axis. So this point here is equal to 3. This is where your second 0 gradient is sitting. And this is the value of x where the local maximum, this x equal to 3 is the local minimum, is the point where the local minimum is sitting. So out of these two, we can reject this one and take this one because this is where our local minimum is sitting. So that is the value of x where your local minimum is sitting. And we're done with this question. So we'll go to the next one, which is 9.3. Okay, so now we're doing 9.3. So let's go. They are saying, use the graph to determine the values of x for which f prime prime at x times f of x is greater than 0. Right? So they want us to use our graph to find the values of x for which f prime prime at x times what? Times f of x is greater than 0. So let's look at this. What is f of x? Your f of x is your function f that we are given, right? This is your cubic function in this case. It's your cubic. The function f, which is a cubic function in this case. Then, next question. What is f prime at x? I said f prime at x is a derivative of f, right? Which gives you a function, which gives you a gradient at a point. I said f prime at x is a derivative of f, right? And it gives you a gradient at a point. So what I would say it's a gradient function. It's a gradient function. Right? Then now, third question is what is f prime prime at x? So f prime prime at x is a function as well. But what does it tell you? Because I told you that your f of x is a cubic function that you are given, the original cubic function, which is this one here. If you derive it, you get f prime at x. And I said f prime at x gives you a gradient at a point. So we can say this is a gradient function. Right? No problem. Then what is f prime prime at x? F prime prime at x is the second derivative of a cubic function. What does it tell you? It tells you about concavity. A function can be concave up or concave down. So we can say it is a concavity function. Concavity function. No problem. So let's go and find the equations of all these functions here. So if we do this, we can say, okay, f of x we're given that is x cubed, right? Minus 3x squared, minus 9x, minus 5, right? This is f of x. This is our cubic function, the one that we were given initially, right? The second one is a derivative, right? F prime at x. We did find the derivative of f prime at x. We found it where? Up there. We found that the derivative of f of x, f prime at x is what? Is 3x squared. Minus 6x minus 9, right? And then now, the second derivative, you will be deriving your first derivative to get f prime prime at x, because if you want the concavity function f prime prime, you need to derive the gradient function, then you get the second derivative. So what do we do? Say, okay, f prime prime at x, we must derive the first derivative to get the second derivative. So it will be 3 times 2, which is 6. On that 2 you subtract 1, then it's just x. Minus 6x. So this is your second derivative, which I call the concavity function. Right? Fine. So this is, I said this is your cubic, you know it. This is your gradient function. This is your gradient function. And this is your what? This is your concavity function. So, they want us to find the values of x, right? Where the product of the concavity function and the function f, which is your cubic function, is greater than 0. So they want us to show them the values of x where you multiply these two, right? When you multiply this one and this one, and their product is greater than 0. That's what they want us to find. So, what we need to do, we need to plot our concavity function. Where? On this thing here. We need to plot it here. Once we plot it there, then we'll be able to compare or find the positions where these products are what? Are greater than 0. So let's do that. So, if you want to plot this concavity function of ours is a straight line, right? So you know the straight line have the x-intercept and the y-intercept. But in this case, to be honest, we're interested in the x-intercept. Because we want the values of x, the y-intercept. Okay, it's fine, we have it. It should be 6 there, the y-intercept. So, what do? We say, okay, let's find the x-intercept. What does it mean, x-intercept? You want to know where is it crossing the x-axis, right? And if you want where it crosses the x-axis, you have half of the coordinates, because you know along that line y is 0. So the coordinates, you have y to be 0 already. So if your y is 0, which is this part is 0, then you can find the x value where your function is crossing. So let's find that point. So 0 is equal to 6x minus 6. Therefore your x is equal to 1. So which is, your x-intercept is at x equal to 1. Which means the straight line, your concavity function, is crossing at x is equal to 1. So where is x equal to 1? X equal to 1 is somewhere here. Right? So let's say this is 1 here. So you have a straight line that have a positive gradient and it's crossing at x equal to 1. Right? So what do? We plot that straight line. Here is it. Looks like this. Here is it up. Here is it down. No problem. So what are you looking for? You want to find you want the values of x where the product of these two functions is greater than 0. So if you're multiplying two functions like this and their product is greater than 0, what does it mean? It's either they're both negative or they're both positive. So what you should look for here, what you have here, this is your f, the black function. The red function is f prime prime. I'm saying the product of these two functions is greater than 0. It's either both, these functions are both positive or both negative. So we'll have to look at that here on this function. So let's do that. You can see f is less than 0 here, right? For values that are less than minus 1. Let's look at the values that are less than minus 1 on the left hand side of minus 1. You can see that both functions, they are negative here. You can see both of them, they are both below 0. On the left hand side of minus 1, they are both less than 0. So this is the position that we're looking for. Because both of them are negative, which means if I can multiply any y values here, the answer will always be positive, which is what we're looking for. So, for values that are less than minus 1, which is for values from minus infinity to before minus 1, the product will be greater than 0. We don't include minus 1. Why? Because at minus 1, x is equal to y, at x equal to minus 1, y is 0. But we want them where the x values, where the our y values are both negative. So that point, x should be for all the values from minus infinity, but before minus 1. That is the first point. Right? Fine. At minus 1, no. Y is 0 there. 0 times whatever value there. It will be 0. So we don't want that. We want our values to be positive. But look now on the left hand side of what? On the right hand side of minus 1. You can see these functions are both negative here. But the red function crossed there. So between this interval, they are both negative. So we should include this interval here. Because, which is between -1 and 1, because both of these functions are negative on this interval because they are both below 0. So if you multiply any corresponding y values or y values that are directly above each other, the answer or the product will be positive, which is what we're looking for. So let's put that interval in together with what? With after -1 to 1. Because on this interval here, between -1 and 1, they are both below 0. So the products of the concavity function and your function will be positive. Then now let's look after 1 now. You can see 1 is positive and the other is negative. So where the signs are not the same, the product will be negative. Then now, so where does this happen? Because you can see this will be positive. So the only position where we can find is where both of them are both positive. So look at this. This is negative, negative, negative. After 5, you can see both of them are now above 0. So their product should be positive again. So you can say together, union, 5 to positive infinity. So those are the values of x for which the product of the concavity function and the function will be greater than 0. Or you can write it in the interval form and say x should be less than -1, but x must not be equal to what? Sorry, your x should be less than 1, but not be equal to -1, or your x should be greater than 5. So this is the same interval. So I prefer this one because I can look at it better, but this is the same interval. So write this way or that way, because all your x values, they are less than 1, right? But not equal to -1, because at -1, y is 0. And your x values are greater than 5. And we're done with 9.3, right? So I'll quickly do the last question, which is 9.4. It will be easy, this one. So let's do 9.4, and we'll be done with this question. So what are they saying at 9.4? At 9.4, you are given a function, p of x to be what? To be f of x plus t, right? I'll say your t is a real number to avoid confusion. Okay. At 9.4, they're asking for which values of t will the graph p of x defined by f of x plus t, where t is a real number, have 2 distinct positive roots and 1 negative root. Let me read this thing again. They're asking for what values of t will the graph p of x defined by f of x plus t have 2 distinct positive roots and 1 negative root. So they're asking, what should the value of t be? What value must they add to f of x such that f of x have what? Have 2 distinct positive roots, right? And 1 negative root. So let's look at f of x now. Here's f of x. If you look at f of x now, f of x, like I said, have 2 negative equal roots. So, because I said you have 2 intercepts here, right? X equal to -1 and x equal to -1. So these roots are 2. They are equal and they are both negative. And what? And 1 positive root. This is what you have on f. This is your situation. At f, you have 2 equal negative roots and 1 positive root. So what they want you to find, what they want you to find now, they're asking you what should the values of t be. So what should t be such that you have what? We have 2 distinct roots and what? And 1 negative root. What does this thing mean? So they want you to have 2 positive intercepts two positive x-intercepts and one negative x-intercept. So they're asking, how should they shift this graph? What value must they add to this function so that it have two positive roots, which is solutions, x-intercepts, and one negative x-intercept. So if you're looking at it here, you know very well that here, your x-intercept is equal to -5, right? And this value here, the turning point, you don't know the value of this turning point, but you know it was at x is equal to 3. So it looks like we might need to find more space to find the corresponding y value. So what we can do, we can say f at 3 is equal to 3 cubed. 3 cubed minus 3 into 3 squared minus 9 into 3 minus 5. So we need a value to this. What is the value to this?
Minus 32.
So the value to this is minus 32. What is this value to this? Is the corresponding x value that goes with this. So we have 3 and minus 32. So these are the coordinates of the local minimum. So you know that there is minus 32 at this point here. So the corresponding y value of this turning point is minus 32. That's what we have. So now they're asking, how many times should you shift this function so that you have one negative root and two positive roots? Right? And your roots should be different. There should be two distinct positive roots. So what should you do? Look, this is f, right? This is f, like I said, the black one. This is f of x. On f of x, if you can add 5 units on f of x, this point would sit here. This point here, 0, would be at 5 up there. And this point, 32, would be maybe at minus 28, if I'm not mistaken. Can you check it out? Say minus 32 plus 5.
27.
Minus?
27.
Minus 27. This sitting, so we said minus 32 plus 5. It's minus 27. 5. So we're sitting here at minus 27. So if I shift this function, you see I add on f of x, which is the original f of x, I added what? I added 5 units. And you can see this point here that was sitting at x equal to 0 will be sitting at 5. And so it was y is 0 here. So its x new x value would be 5, right? And so its new y value would be 5 here. And this point would be sitting here at 0. And this point would be here at minus 27. So if you look at the plotted version of the new function, which is f of x plus 5, I'll make it a different color. Maybe let me make it blue. I'll make it blue. So a new function will look like this. That is shifted 5 units upwards. It will look something close to this. Are you happy?
The last point there.
Which one?
You shifted to the left a little bit.
Did I move a point? Which one?
The last one.
This one?
Yes. So it will go up.
Oh, okay. You mean to the right?
Up.
You mean this part here? This one?
Yes, it will be shifted up.
Oh, okay, its position. Okay. So its position should be up here, sorry.
Still on along the same x.
Along the same vertical line. Okay.
Yes.
Okay, that is 5. So the new function will look something similar to this. So this is a new function now. This is f of x plus 5 units. Now, if you look at the roots of this new function, you can see one is negative there, and the other is 0, and the other is positive at this point. So you have 3 distinct roots. They're all different, but they're not following the same orders as that. We're ordered that they should be, we have 2 distinct or 2 different positive roots and 1 negative root. So in that case, if we want this function of ours to have two positive roots, two positive different roots, this point, this point, our second intercept to be on the right hand side of y-axis. We want this function, this blue function, to cross on the right hand side of the y-axis. But look now, when we shifted 5 units upwards, it did sit exactly at this point, right? But if we shifted more than 5 units, look, if we shifted more than 5 units, this point will be above here, which means it will cross before y is equal to 0. So what we need to do, we need to shift this value, this function of ours, more than 5 units upwards, right? But at the same time, we should not shift it more than 32 units upwards. Because if you shift it 32 units upwards, it will sit exactly there. Are you still with me? And in that case, you will have now one negative root and two equal positive roots, which is what we don't want. What we want exactly two positive distinct roots and one negative root. So in that case, if you want to obtain that option, you must shift your function more than 5 units upwards, but less than 32 units. So that the turning point is always below the x-axis. So in that case, your value of t at which you should translate this function by, it should be something along the lines of, I don't have much space, but I'll write it here. This is the final answer for 9.4. So what you should have, your t, which is your shifting factor, it should be greater than 5 units. Maybe I should find some space. I won't need much, just here. Just to finish 9.4. So, if you want two positive distinct roots, this function should shift more than 5 units upwards. So your t, which is the value at which you are translating this function upwards by, it should be greater than 2 units, right? But at the same time, it should be less than 32, because if it should be greater than 5 units. Yeah, this should be greater than 5. What does this mean? Because it was sitting here at minus 5. Shifting it 5 units pushes it here at 0. But shifting it more than 5 units pushes it above 0. And if this part is above 0, which means you will have another root on the right hand side of the y-axis, which will actually be positive. And then now, but that should be less than 32, because 32, if you shift this 32 units, it will sit exactly there. Then now you have a problem of two equal roots, which you don't want. You want your roots to be two unequal distinct roots. In that case, it will have to be less than 32 units. So this is your final answer for 9.4. And I hope it does make sense to you, as it does to me. Any questions?
What happens if we include 5?
Sorry?
If we include 5, what's wrong?
Including 5. If you including 5 now, you're saying when it's sitting here, you have two distinct roots, which should not be true, because the goal is to obtain two distinct roots, right? But now, if you're sitting here, this is 0. So you have one root that is negative, one root that is 0, and one root that is positive. It's not achieving the condition that we're trying to get.
Can you explain the word distinct?
Distinct means different. When you say you want two distinct roots, you say you want two different roots that are positive, which means those should be your positive x-intercepts. So which means you want your x-intercept to be on this side, which means this point should be above there, so that this function crosses maybe on this side. And we're done here. Thank you for watching. Cheers.